Okay, here we go yet again. Last section of chapter 11. So, very difficult chapter, lots of tough stuff in this chapter. Hopefully you're doing okay. Notice the homework as well as the review questions for the entire chapter. There's lots of questions in there. The main thing here is to give you as much practice with this as you possibly can. The more practice you get, the better you will understand it. So I know it seems like there's lots of questions and it's annoying to do all the work, but that's going to help you in the long run with this tough stuff here. Okay, let's review some of the things we talked about with our parallel and our series circuit. So remember that here's an example of a diagram of a series circuit. Notice one direction only for electrons to travel on. Remember that these lines represent wires. This first symbol here is a switch, and then these two symbols down here are light bulbs, and then this is our single cell battery. We see our negative terminal and positive terminal there. So electrons are going to go from the negative terminal, follow along here. They can't pass through this open switch, so none of these light bulbs will be on. But if the switch were closed, then the electrons would flow through this bulb, and then return back to the positive end of the cell. So only one path. If one load fails, it stops the flow of electric current everywhere in the circuit. So the switch is open, neither of these lights are working. Parallel circuit, we see that our diagram has all the same components. One cell, battery, open switch, two bulbs. But I've put the bulbs in a different location, putting them now in parallel with each other. So this is a parallel circuit, but only the bulbs are connected in parallel because we see a junction point right here. This has two options for electrons to go through. Every single point in a series circuit only has one option, only one turn for the electron to make. You notice that electrons could go straight or they could turn to the right. That is how we know that this is a parallel circuit, and that's how we know this is where the parallel junction gets provided. This switch here, though, notice where this switch is in the circuit. This switch is open, both bulbs are off because it's at the front. If we were to put this switch along one of these parallel paths, so putting a switch over here, you notice that if we have an open switch on this pathway, if this switch were gone, then this light bulb here would still light up because the switch now is connected in parallel. But as the way it's drawn, this switch is not in parallel. It is in a parallel circuit, yes, but it is not connected in parallel. Hopefully, seeing the difference in there will be helpful for it. So two more paths for electrons to follow, like we talked about. If one load fails, the other loads will remain operational. There are alternate pathways. So another way of putting that is, again, if this switch were closed, so electrons could flow, but then if this bulb were to be burnt out or disconnected, this bulb would still work fine because we have multiple options for directions for electrons to go. Okay, a little review about the two of them. Let's talk about the relationship of current in a series circuit. We mentioned a little bit, we talked about what current was, we talked about how to calculate current with some examples. Now we're going to take a look at this specific case of a series circuit as well as a parallel circuit because there's an interesting relationship between current, voltage, and resistance at different points in a series circuit. So remember what a load is just anything that's connected that transforms electrical energy into some other form of energy. And let's see how these loads are connected, and let's see how the current behaves in these different loads. So the current, remember symbol I, is the same at all points in a series circuit. This is an interesting little relationship. You can summarize it with this formula down here, that the uppercase I, or the total current, is equal to the current at load 1, load 2, and load 3, which in total is equal to 2 amps. if we look at our circuit down here, we have a 2-cell battery, negative positive terminal. This A is an ammeter connected, obviously in series. Remember, ammeters have to be connected in series. We have our one wire going through the ammeter up here to our first load, which is our first light bulb. Then we have another ammeter connected to another load, light bulb number 2, another ammeter, and then light bulb number 3, the ammeter after it, and then connecting back to the terminal. This first ammeter, notice how there's no loads before it. Energy directly coming from the power source goes to this ammeter, measures the total current coming out of the power source, in this case, a 2-cell battery. 2-cell battery is providing 2 amps of current. I know the font is different, but this is an uppercase I. Notice how it's a little bit different here, how the I looks more like a regular I, whereas this one just looks like a straight line down. I know that's a little tricky, so please just remember that this straight line is an uppercase I, okay? Power going directly through this first ammeter gives us 2 amps. Electrons then move through and they go into this first load. And then once the electrons come out of this first load, this ammeter here is measuring the current at this point in the circuit, directly after this first load. What do we notice though? It's the exact same current that was coming out of the battery. Then electrons move to the second load, this light switch here. This ammeter measures the current after now 2 bulbs, so 0.2 in the circuit. That's why it gets this little subscript 2, because notice that this is 0.1, this is 0.2, and then this is 0.3, because this is the total. This ammeter is first, but it is measuring the total energy coming out of the battery. 2 amps at 0.2, and then again a third load or third bulb with another ammeter measuring the exact same current. This gives us this little relationship here, that the total, right, is equal to the first, equal to the second, equal to the third, and which are all equal to 2 amps. That's why we have all these equal signs, okay? The current at every single point is going to be identical to whatever the total current is for a series circuit. The same amount of electric charge, or the same number of coulombs, that passes through the source in a series circuit will pass through each load, right? Because remember that a current talks about the amount of charge passing a point in a given amount of time. So what this tells us is that in a series circuit, the exact same amount of charge passes through each point in the same amount of time. So our series circuit has an unchanged current, and we express it with this relationship. IT equals I1 equals I2 equals I3. Therefore, if I gave you a question and said, here's a series circuit, this light bulb has a current of 5 amps, what's the total current? Then you should be able to tell me, oh, it's 5 amps. So that's sort of the handy thing about series circuits with current, is that they're very easy. If you know any information about the current for any load or total, whatever it is, you know the current everywhere else. So hopefully that is an easy thing. Let's talk about the voltage, because voltage is a little more complicated, but not much. So the potential difference, or I'm just going to call this voltage, across the source must equal the sum of the potential difference across each load in a series circuit. So notice that it's a little different. It's not the exact same, but we still do have a connection between the total voltage as well as the voltage across the individual loads. So again, here's another example. What you notice is this is still a series circuit. I thought I was getting ahead of myself. Still a series circuit, right? This bulb, this bulb, this bulb, all connected in series. But you might say, but wait a sec, sir, the voltmeter is connected in parallel, right? It's connected across. So what type of circuit is this? Remember that voltmeters and ammeters don't qualify as loads per se, because they shouldn't be converting any of the electrical energy. The energy should just be passing directly through, and we should be getting a readout for it, or it should be using very minimal amount of energy. Not like a light bulb, which we want specifically to convert that energy, whereas the voltmeter and ammeter, we don't want them to convert that energy. So they're not technically a load because they shouldn't be converting the energy in any way. All that is to say that the ammeter and the voltmeter are just helping along, right? They are sort of extra to the circuit, and they're telling us something about the circuit. The circuit itself in this example here is series, even though we have voltmeters connected in parallel across them, okay? So please don't think that this is a parallel circuit, because the overall wiring of the circuit is in series. If some of these loads were connected in parallel, then we would be looking at a parallel circuit. So we'll get examples of that later on, but please, this right here is series. So what we do is I make my circuit, okay, and then I connect a voltmeter across the battery, right? I put one lead directly before, one lead directly after. I could always, do I have a picture? I can always connect 2 points. So just sort of jumping ahead here, if I were to connect a voltmeter, let's say, across the battery like this, I could connect it directly to like the battery itself, right? Like it doesn't really matter as long as it's on either side. So 1 voltmeter connected across tells me, okay, voltage is 10 volts. Okay, that's the total voltage. That's how much voltage this battery has, right? And you could read that obviously on the battery itself as well, because it'll tell you the voltage. So in this case, for this example, it's 10 volts total. Then we go along to the first bulb, okay, the first load, connect a voltmeter across, and its reading tells me 5. Then I put a voltmeter across the second bulb. That voltage is 3, and then the last one voltage is 2. Notice 2 things. A, that these numbers are all different, okay? So in a series circuit, the voltages will be different, but they all will add up. 5 plus 3, 8. 8 plus 2, 10. But they have to add up to the total voltage of the battery, of whatever your power source is. You can't have more or less voltage than whatever you're supplying, if that makes sense. Similar to this, because we only have, this is like the maximum current that it can have, but the current stays the same. Whereas in this case, we can have differences. We can have differences, but they will all add up to the same total, right? So kind of makes sense. It's a closed pathway, right? Electrons, we only have a certain amount of energy. We can't give this circuit more energy than the battery can provide. That doesn't make any sense. And it also doesn't make any sense that we would lose more energy than we would have, because that energy has to go somewhere. It can't be created or destroyed, so it has to be doing something. The other thing I wanted to point out, notice that the first load has 5 volts. It has the most. The second bulb has only 3, right? Less than 5. And then the last one has 2, less than the other 2. So you can see that the voltage will be decreasing as we go through the number of loads in series, okay? And that makes sense also. We talked about that the energy that the electrons have will be decreasing. So this is the difference between the two. I know it seems very confusing. The total, same thing with our current. The total amount of charge is fixed. We can't have any more. Since we only have one direction for all that charge to pass through, the current's going to be the exact same, right? We're not talking about energy in this case. We're just talking about the pure number of electrons, basically, right? Since we only have one direction to pass through, all the electrons have to pass through each of these bulbs in turn. So if you picture it like a marathon, like a bunch of people at like a race, right? As they run through, I've drawn 1, 2, 3, 4, 5 dots. All of these 5 dots will have to pass all of these points, right? So when I get back to the battery, these same 5 dots will be back here, if that makes sense. Whereas talking about voltage, we're talking about energy. And so since we only have one way to go, we're actually going to be losing some energy as we pass through each of these points, right? Because those same electrons have to go, they all go through this bulb, but they're going to be a little bit more tired. If you picture these as little hills, right? If our analogy of people running a race still works, if they're running a race, it's like they're going to be tired after this point, but they're going to be more tired further along the race, and they're going to be at their most tired or their lowest energy at the very last hurdle, whatever, right? The very last point before they reach the finish line. So they lose energy as they go along, if that helps, just to see the difference between the two. So the relationship then is that V total voltage, is equal to the sum, right? V1 plus V2 plus V3, or however many loads there are. You add all of those guys up, it'll tell you the total. So each load uses a quantity of energy from each coulomb that passes through the load before the coulomb moves along the circuit to the next load. So the coulomb, remember, is the charge, right? We're using some of that energy of that charge. The quantity of energy used by each load must add up to the total energy that leaves the source, right? Another way you can, yeah. So let's just go with that. Hopefully that makes sense. So you can see two relationships. In a series circuit, the current always going to be the same, but the voltage, you'll have to add up the individual voltage of all those loads to find the total voltage. Again, so I could give you a similar question, like I mentioned for the current. I could tell you the total voltage, and I could give you some loads, and you could figure out what the voltage would be for each respective load. Now, that being said, you would need a little bit more info. I couldn't just give you like 3 blank things and say, tell me what the load is of each one, because you don't know how much energy is going to be lost, right? Like, you know that they'd have to add them up, and you know that they'd have to lose. So how do you pick 5, 3, and 2? Like, you wouldn't be able to do that. So I could always give you like the total. I could give you the voltage here and the voltage here, and then ask you for this one, right? I could say, here's the total voltage. Of the 3 loads, you have one that has a voltage of this and another one with a voltage of that. What's this voltage here? And to figure that out, just 10 minus 3 minus 2 will give you 5. With me on that? So you have a way to figure out the voltage and the current in a series circuit if I give you a little bit of info. Combining that with the Ohm's law we talked about, remembering that resistance was equal to the voltage divided by the current. Using this relationship here, Ohm's law, we can add this now to a question like this. If I gave you a series circuit and told you the total voltage, asked you to find total voltage and 2 voltages of the loads, asked you to find the voltage here, I could also say what's the current of this bulb. And if I gave you the resistance of that bulb, you would find the voltage by 10 minus 3 minus 2 to get this, and then you could use Ohm's law to calculate the current for that bulb, right? So there's multiple things that we could be asking you to do now to use some of this math. So you can see why this is a trickier one. And I'm going a bit slower on this lesson just because it is difficult to understand. So hopefully you're with me. Loads in series now. No, sorry, same thing, still in series. Let's talk about the resistance and how that works between each one. So adding more light bulbs in series to a circuit increases the total resistance of that circuit. This has an effect on the intensity of light bulbs in the circuit. So the more bulbs we add, they will have a little bit of resistance to them, so it's going to slow down the overall resistance as well, right? And that means that if we add more bulbs in series, then each bulb gets dimmer the more bulbs we add. So if we have 3, they'll have a certain brightness, but if we add 4, then all of them will be dimmer, versus if we took a bulb out, removed a bulb completely, but then replaced it with wire, so it's no longer in the circuit, then the remaining bulbs would be brighter. The total resistance in a series circuit is the sum of individual resistances for each load, so that the total resistance is equal to the resistance of each load added together. So this is just like the voltage that we talked about, right? Voltage, this is the same relationship as the voltage, right? We can find the resistance of each of these because if we know the total, we can find the resistance of the individual ones as well, right? We're not using any kind of meter to measure these, but we can, as well as if we know the material, the temperature, remember those things that affected resistance. If we know all of those, then we can figure out the resistance as well. And here's just a diagram showing you how it goes from being very bright to being a little dimmer to being more dim as we add them all. So the more bulbs there are, the more resistance there is in a series circuit. So voltage and resistance have the same relationship. Hopefully that's helpful as opposed to confusing. And then here's a nice summary slide for all of them. So these symbols here are resistors, right? And these I's are just showing the current at a particular point. So here's the this circuit here shown in this form, right? I have a battery here, okay? And negative terminal, so electrons go to the left. This means, it's not written here, but I have an ammeter in series. So this wire goes directly to the ammeter, then another wire comes out, goes to our first bulb. So this is number 1. And then this is number 1 here. Okay, for our bulb, sorry, resistor. This is a resistor. This is number 2 resistor, which is this here. This whole squiggle line thing, right? That's the symbol for resistor as well. And then the third resistor here, which is this whole squiggle line, just to show you. Okay. And we have little current measurements, but we actually don't see any ammeters in here. Let's talk about the voltmeters now, because the voltmeter is actually connected in parallel, right? So this is, we have 2 branches, we have 2 wires. So the electrons can go from, they'll split, right? They'll go from the negative terminal through the ammeter and then through the rest of the circuit and return, but they'll also go up this wire here through the voltmeter back to the positive. So there's a branching point for some of the electrons to go through. I've connected my voltmeter in parallel across the bulb. I measure the total voltage of this, and then I can see the voltage of each of these resistors, right? Again, voltmeters, with voltmeters connected in parallel. So when we get to this junction point, electrons can go this way and then return to the other side before they continue and go along this way, if that makes sense. So we have 2 pathways that these electrons are going through, and that's how we get readings on the voltmeter. And then when they're done here, they return back to the positive. So it's still a series circuit. Just wanted to show you all the connections for it there, to show you what they all are. And each of these loads has their own resistance, has their own voltage, and will also have a current, right? The reason that the current's in here is because this ammeter, if I wanted to measure the current at point 1, I would disconnect it here, right? Disconnect there. I would put this wire just right to the bulb, and then I'd put the ammeter right here with a connection in and out through. I know that's really messy, but just to show you. So basically the ammeter would be disconnected. It would move to like this point first, measure the current, then we move it there, measure the current, move it there, measure the current afterwards. Just a little summary. Okay, hopefully you're doing okay. You can pause the video, take a break, do whatever you want, but I'm gonna keep going. Let's now talk about loads in parallel circuits and how this works, because now we're gonna shift everything, which is the confusing part. I personally have a lot of hard time remembering these rules because I always get them confused. So do whatever you need to do to remember the differences between them. Okay, let's talk about the current in a parallel circuit now. So there's a different amount of current measured through each load that's connected in parallel. However, the sum of these values is equal to the current coming from the source. So you notice that we're shifting our definition now. So current in a parallel circuit has the same relationship that voltage did in a series circuit. Okay? Simple stuff, but very confusing, especially because you might be hearing this stuff for the first time. So please don't beat yourself up if this is hard. You might just need to watch these things or read about it a couple times before you get the hang of it, because you're using a lot of new terms, right? Like current, voltage, all that stuff. Okay, here is our parallel circuit. It's parallel circuit because all the loads are connected in parallel. So from the negative terminal, we have one direction through this ammeter. Again, only one place to go, so still in series here technically, but look, we get to this first point right here and we have a choice. Go straight or continue down along this path. Parallel circuits split up the amount of charge that goes through each of these points. You can think about it like water. Some water is traveling in this way and some water is traveling sort of in this way. So that means that we have a fixed amount of water, right? If we have a battery, we only have so much, right? Like water in a tank. Picture that, not like a lake or an infinite, you know. So water in a tank from here. Some of the water has to go here. Some of it has to go down here. We're splitting up the amount of water that would normally be traveling just along one way. Okay, so this pipe, using the water analogy, will be a little less full if it's connected in parallel. If it's connected in series, all of the water has to go along one pathway, but right, you can see that we're splitting it. So the amount of charge gets split at each of these junction points, just like the voltage did before. So what we notice is if we put an ammeter, if we connect the ammeter in series still, but along these different pathways, we get different readings for the current. But what we notice is once all of these, but then all the charge when we get back to this junction point here, all of the charge has returned, right? And then now basically in this red section and then in this red section here, this is the full charge returned, which is our 12 amps. So it's 12 amps the whole way. We get to this point here, 5 amps of charge move along this one pathway, and then 12 minus 5, 7 amps of charge move along up here, okay? But then we have another junction point, and we see that of that 7, 4 go this way, and the remaining 3 just goes up here. Once we get here, we now have 7 amps of charge again, and then once it hooks up with the 5 back here, we're back to 12. And then that just process sort of repeats and repeats, right? So that's how that works. Same. So this equation is the same, but now it's for current because we're in a parallel circuit. So we're switching gears here. It's very, very difficult to get, but you'll get the hang of it. So different number of coulombs, remember that's charge, will travel down different pathway of a parallel circuit, but the total number of coulombs, right, of charge within the circuit is equal to the number of coulombs that came from the source. So again, just like the voltage, we can't go above or below this total here. This is what we have to work with, and we split it up as we go through. So parallel circuit, the current now is equal at each load in the circuit will be equal to the sum when you add them all up will be equal to the total current. Okay, total current is equal to the sum of the current of the individual loads. Now again, let's do the same thing. Let's talk about the voltage. All coulombs, so all the charge are given the same amount of energy from the source. So what does that mean? In this case, the voltage now is the exact same at every single load in a parallel circuit. So what have we done? We've flipped the definitions. If we go back to current in series, the current is the same everywhere in a series circuit, and the voltage, you have to add them up in a series circuit, okay? Now, in a parallel circuit, the current is the same everywhere, and we have to add up. Terrible, F minus. The current, we have to add, voltage is the same, right? We just flipped it. With me? Hopefully. Okay, let's go through the voltage again then. All the coulombs, all the charge do not travel through all loads that are connected in parallel, right? So all the charge gets split like we talked about. But regardless of the path that the charge takes, the energy each coulomb carries can be used by each load, right? So basically, this is kind of the interesting thing is when the current is splitting, it still needs the same amount of energy to do its thing, right? So that each of these bulbs can work properly. They need the same amount of energy. So the current will split up, but it'll split up in such a way that the energy can be the same at each bulb. So parallel circuit, the potential difference of the voltage across each load is the same as the potential difference across the source, okay? Let's talk about the connections of these voltmeters because this will be important. Here we have a parallel circuit because each of these bulbs is connected in parallel, right? Junction point here, not technically not there, right? But junction points here and here for choices of direction, right? Notice here though that this voltmeter is connected in parallel across this 2-cell battery, but then this voltmeter is also connected across this light bulb. So we're this is like an inception thing. It's a parallel circuit with each voltmeter connected in parallel as well. Hopefully you can see that in this. That will definitely help when you're making these circuits, okay? So it's a parallel circuit when we look at the bulbs, and then the voltmeter is also connected in parallel. And we see that, okay, let's measure the voltage of the battery is 6 volts, and then it doesn't matter where we put the voltmeter, every single bulb will give the exact same reading. So the relationship is that the voltage is the exact same at every single load in a parallel circuit. You don't need to remember, you only have to remember 2 forms of an equation, right? Either everything's equal or you have to add them up to get the total. It's just remembering which one's which in which situation. That's the hard part. And that is very difficult, I find. Hopefully these explanations help you visualizing them. The resistance in parallel we don't need to focus on as much because it does some strange things. And at this level, we don't need to worry about it. All we need to know is that maybe counterintuitive to what we would think, the resistance in parallel will actually do something different than what we've seen before. It'll actually be less. So the more resistors, so the more resistance we put into a circuit, so they can be loads, they can be resistors themselves, whatever. The more resistance we put into a parallel circuit will actually decrease the total amount of resistance, which seems very strange because we're like, well, wait a second, in in parallel, in series, you add them up because light bulbs get dimmer. It makes perfect sense, right? Well, we're not going to talk about the reasons for it, but if you connect these guys in parallel, because they have the same energy going through them, they'll have the same brightness. And the resistance, like we said, does some weird things. The relationship here is a bit more complex, so again, we don't need to focus on it. All you need to know is that the total resistance will be less than the resistance at this load here, right? And then the resistance will also be less than the resistance here and the resistance here, right? That's the one thing that we have to know. So the total resistance in a parallel circuit will be less than the resistance of any of the individual resistors. That doesn't seem to make a lot of sense because you're like, the total is less than the sum of its individual parts. It's just how the math works out, and it's just how this functions. So that's all we need to know about resistance. And again, a summary sheet for the relationships of current, voltage, and resistance for a parallel circuit. The focus for parallel circuits really on voltage and current, whereas the focus for series is all 3. So the series circuit, we can focus on all 3 because these three relationships are pretty easy to remember, and these 2 relationships easy to remember. This is the trickier one. So if you're not as comfortable with this, that's okay. You should still know this as best you can, but if you're struggling, really focus just on these 2. That'll be the important part. A little less emphasis on the resistance in parallel, but we'll have an equal emphasis on current voltage in both parallel and series, right? Okay. Let's keep going. So I know this is a long one, but you can pause if you need to. Current is measured using a device called an ammeter, which we talked about. They have to be connected in series to measure so that everything goes through it, right? The red probe is connected to this is how to actually, this is a different specific ammeter. Anyways, measures 10 amps. Black probe connects to the ground. You just have to connect the red and the black if you're using these. Red and black are used in electricity to so that you don't have to. It's just colors of the casing of the wire, right? So that you can tell, okay, which one's positive, which one's negative, quote unquote. It'll help you know sort of which ones are going in, which ones are going out. If you used all the same color wire, then it might get confusing. It's not necessary. Though, right? And then how to connect a voltmeter. Remember, voltmeters need to be connected in parallel. Okay. So important thing here is the summary charts, do your best, do the homework there. Hopefully, uh, hopefully that works. I know it's a tough one. This is a tough unit. Let me know if you have questions. All the best, guys.